The view of the sun's path depends only on your position on Earth. At the poles, polar day and polar night last for 6 long months. In the hot tropics, the sun passes exactly through your celestial zenith twice. Astronomy teaches us to understand eternal rhythms of heat and light in space.
Welcome! Today, we are going to conduct a rigorous analysis of the sun's apparent daily motion as observed from various latitudes on Earth. We will see how an observer's position fundamentally alters their perception of the sky, from the extreme poles to the balanced equator. Let's begin with the fundamental question that frames our entire investigation. Why is it that the very definition of a day, the sun's path, and its duration shifts so profoundly as we change our location? The answer, as we'll see, lies not in the sun, but in our own perspective on a tilted, rotating planet. We will proceed systematically. First, we'll establish our celestial frame of reference. Then, we will undertake a theoretical journey, beginning at the North Pole, moving south to the Arctic Circle, through the tropics, and finally arriving at the equator. We'll conclude by synthesizing these observations to define the Earth's astronomical climate zones. Very well. Section 1. The celestial framework. Before we can analyze the sun's motion, we must first define the coordinate system we use to map the sky. I want you to start by picturing the sky not as an empty space, but as a vast, hollow sphere that surrounds the Earth. This is the celestial sphere. It's an ancient and incredibly useful concept, an imaginary canvas onto which we project the positions of all stars, planets, and for our purposes, the sun. Now here is the single most critical variable for our entire analysis: declination. Just as latitude measures your position north or south on Earth, declination measures a celestial object's position north or south on the celestial sphere. Due to Earth's axial tilt, the sun's declination changes continuously throughout the year, and this annual migration is the engine that drives everything we're about to observe. Let us begin our journey at the most extreme observational point, the North Pole, latitude +90 degrees. Here, the phenomena of day and night are stretched to their absolute limits, providing a stark illustration of our principles. For an observer at the North Pole, the celestial equator lies perfectly on the horizon, a complete 360-degree circle around you. What this means is that the entire celestial sphere is divided into two permanent halves, the visible and the invisible. Any object with a positive declination is in the upper hemisphere and will circle endlessly above the horizon, never setting. Any object with negative declination is forever hidden below. This unique geometry dictates the sun's behavior. Around the vernal equinox, the sun's declination becomes positive, and so it rises. For the next 6 months, it spirals slowly higher in the sky, circling the observer in a single unbroken day. On the autumnal equinox, its declination turns negative, and it dips below the horizon, initiating 6 months of polar night. On the summer solstice, the sun's declination reaches its maximum positive value. For the polar observer, this translates directly to its maximum altitude. It doesn't appear high overhead, but rather traces a perfect circle parallel to the horizon at an altitude of precisely 23 degrees and 26 minutes. Conversely, at the winter solstice, the sun reaches its maximum negative declination. It is now at its lowest point, circling just as far below the horizon as it was above it 6 months earlier. It's a perfect mirror image symmetry. We now travel south to a critical theoretical boundary, the Arctic Circle. Its position is not arbitrary. It is a latitude defined with astronomical precision. The Arctic Circle is the latitude where the phenomenon of a 24-hour day first appears, but for only 1 day per year. On the summer solstice, the sun's daily path is just tangent to the horizon. At midnight, its lower limb grazes the northern horizon, and it immediately begins to climb again. 6 months later, the opposite occurs. At noon on the winter solstice, its upper limb just grazes the southern horizon before sinking again. Our journey continues south to another astronomically significant line, the Tropic of Cancer. Like the Arctic Circle, it is defined by a unique solar event that occurs on a single day. The zenith is the point in the sky directly above an observer, an altitude of 90 degrees. At the latitude of the Tropic of Cancer, on the summer solstice, the sun's declination perfectly matches the observer's latitude. The result is that at local noon, the sun culminates not to the south, but directly overhead, passing through the zenith. This 90-degree culmination is the defining characteristic of the tropics. If you were standing on this line on June 21st at noon, a vertical pole would cast no shadow. This singular event is what separates the temperate zones from the tropical zone. Finally, we arrive at the equator, 0 degrees latitude. Here, the relationship between the observer and the celestial sphere creates a perfect symmetry, a state of astronomical equilibrium. At the equator, the celestial poles lie on the northern and southern horizons. This means the celestial equator forms a perfect arch passing from the eastern horizon through the zenith to the western horizon. This geometry ensures that the daily path of any celestial object is bisected exactly in half by the horizon. The consequence? Every object is above the horizon for precisely 12 hours. Day and night are always equal in length. But while the duration of daylight is constant, the sun's noontime position is not. On the 2 equinoxes, its declination is 0, so it passes directly through the zenith at noon. For the rest of the year, its culmination point shifts. For half the year, it is in the northern sky at noon. For the other half, it's in the southern sky. Now, let's synthesize these distinct observations. We can now see how these specific solar behaviors at key latitudes form the basis for the Earth's primary astronomical climate zones. You see, it all connects. The cold belts, or polar regions, are defined as any latitude where the sun can become a non-setting or non-rising body for at least one day. The temperate belts are where the sun always rises and sets, but its declination never matches the latitude, so it never reaches the zenith. And the hot belt, the tropics, is the region where the sun not only rises and sets daily, but will pass through the zenith on at least one day of the year. These are not meteorological definitions, they are astronomical. So we conclude by reflecting on this. We have discussed pure celestial mechanics, angles, coordinate systems, and orbital parameters. And yet, these abstract geometric principles are what ultimately determine the distribution of solar energy, the patterns of the seasons, and the fundamental environmental conditions that have shaped all life on Earth. A truly profound connection to consider.
Thank you, friends. Strive for understanding and become wiser. See you soon.